Hello and welcome everybody. Today in calculus we are going to conclude on how to solve for the first order differential equation. So in the past you have learned how to solve for differential equation using separable variable. So that means to get all the y's on one side, get all the x on one side, and then afterward integrate both sides accordingly. Now that is nice and simple for the most part, but what if you cannot separate your x and y's together? What if you have an equation where, kind of like the bottom over here, as I gave it as an example, where there's just no way to get all the x on by itself and get all the y's by itself then. So how do you solve for that then? So that's what we're going to be talking about for today. And hopefully, this will be something that will be useful and especially kind of like a little gateway into I guess the next course, which is called, well, differential equation actually. So let's go ahead and talk about how to actually solve for something like this then, okay? So here, as I said, the first order differential equation has a form that looks like the following, where you have y prime, and then where you also have y, and then maybe some equations along the line, the way that is in terms of x or t. Now, this equation, it should pretty much looks kind of like a linear equation in a sense, where you have y prime and y, because those are kind of like your first order. And then you have like, kind of like some other stuff along the way. In terms of what we've solved for in with applications, we've been looking at those equations where, sorry, not equations, but those applications where you have, like, say, water goes into a tub, and then you have like some sort of I guess like salt in the solution, and then as the water goes in the tub, the water also goes out the tub, and it also drains some of those solutions along the way. And then the question is, well, how much salt is going to be in there along the time? So say, for example, you have something like, say, water going in, but then it's not going in at a consistent rate. Maybe, you're only letting in a little bit of water at a time, and then a little bit later, basically some sort of function then. Okay, so what if your inflow is not consistent in that case? And that's where it leads into this type of differential equation. Now, just to show you that what I have right here is not something that you can just isolate y, we can go ahead and try to do that on the side right now. So take my equation right here below, dy dx plus 2xy, and then it's equal to x minus 1. Now, if I multiply dx to everything, just so we can kind of like see if we can separate it, we will get dy plus 2 over dx, and then we have y times dx is equal to x minus 1. And so note that because on the other side, I don't have any dx's. Actually, wait, I do have some dx. I can actually go ahead and put over there for right now. And then if I move everything over to the other side, then dy is equal to x minus 1 minus 2x times y, and then all multiplied by dx. And so note how, because on the right hand side there is a y that I cannot get to the left hand side algebraically, this is not something that I can separate. So the question is then, well, how do you solve for something like this? So here, let me go ahead and erase all of this stuff over here on the side first, and let's go ahead and start from the very beginning. Now, this is what I'm going to do. Now, I'm going to go ahead and multiply everything by x squared. So the question is, okay, where did I get that x squared from? Because that seems like something I just kind of pulled out of my thin air, which I will explain in just a little bit. But watch what happens when I do so. If I multiply this whole equation by x squared, right, then the left-hand side, you'll get x squared multiplied by y prime, and then we also have plus 2x, and then multiplied by y, and that's going to be equal to, for the other side, you're going to get x cubed minus x squared. Now, you'll notice that doesn't really look like much, and I kind of use a different kind of pen for the stuff that's on the left-hand side. And that's because I want you to be able to recognize the following then. Looking at the left-hand side, you'll notice that this actually looks like the result of a product rule. Okay, that looks like the result of a product rule. You'll notice that here we have, like, say, f, and then this is going to be g prime, and then plus f prime multiplied by g. And so the product rule, well, if I were to write the product rule out, this is supposed to be the derivative of f times g. Okay, so if I were to be able to recognize it that way, then I can actually solve for what we have. Now, once again, the left-hand side is the result of a product rule. And the product rule, when I'm taking the derivative of, what I'm trying to find out the original equation is, well, it looks like it's going to be x squared multiplied by y, right? Because if I take the derivative of that, you would definitely get then what we had previously above. Now, on the right-hand side, we're just going to go ahead and keep things the same thing. So we'll have x cubed minus x squared. And then now, in order to get rid of that prime, we're going to go ahead and take the antiderivative of both sides then. So x squared multiplied by y, because the derivative and the integral cancels each other out. On the right-hand side, you're going to end up with 1/3, oh, sorry, not 1/3, it's going to be 1/4 in this case, okay? So 1/4 x to the 4th minus 1/3 x to the 3rd, and then plus some constant c. And once again, since I'm trying to solve for y, we're just going to have to divide both sides by the thing that's in the way. So my final answer is 1/4 x squared minus 1/3 x and then plus c divided by x squared. And usually we can solve for c if we're given some sort of a initial point to plug in. But there you go. Now we actually have something to solve. But still, the question remains, how did I know to multiply everything by x squared? Because that just seems like black magic for the most part. So here is where we're going to derive this first order differential equation. We're going to derive something called the integrating factor. And that integrating factor is basically the x squared that we just came up with. The question is, how do we know what's this integrating factor? So then that way we can multiply it to get a nice equation that we can actually solve. So here is my differential equation, my first order differential equation. So here's what I'm going to do. I'm going to go ahead and, as we said, multiply both sides by I of x, where I of x is supposed to be my integrating factor. Okay, so it's not, actually, I'm sorry. I of x is not the integrating factor, it's a part of the integrating factor. Okay, so, just kind of like the same as before, I want to be able to derive this equation of I of x that I need to multiply to both sides. So I'm going to multiply that to both sides then. If I do so, then I am going to have I of x multiplied by y prime plus I of x multiplied by p of x times y. And actually, I think I made a mistake because that second part shouldn't have a prime in there. So hopefully I can kind of get rid of that. Well, hopefully it'll eventually show up. And then that is going to be equal to q of x multiplied by I of x. Okay. Now remember, I want to be able to recognize the left-hand side as a product rule. Okay, I want to recognize the left-hand side as a product rule over here. So I'm going to look at this as kind of like, f and then g prime and then plus f prime and then g. Now you can see that clearly g prime and g are basically the same thing, but you'll notice that f and f prime, that's going to be I of x, and then f prime is going to be this guy, I of x times p of x. So what that means is I need to find a function, okay, I need to find an equation where the derivative is basically a part of itself, okay? I need to find an equation where the derivative is itself. So this f equation is going to be actually, I guess, here, let me just kind of write that out first, okay? So f is equal to some function I of x, and then f prime is going to be equal to I of x multiplied by g of x. Sorry, not g of x, but p of x. So if you think back to, okay, well, what you did in calculus, where the derivative is itself, the only thing that comes to mind is it's going to have to be some sort of exponential equation, because that's where your derivative is itself, plus a little bit more, well, actually times a little bit more because of the chain rule. Okay, so let's see if we can kind of derive that then, okay? So over here on this part, here's what I'm going to write then. So I'm going to go ahead and say di dx is supposed to be equal to I of x multiplied by p of x. So note how I said that the derivative is supposed to contain itself and then also multiply by some sort of extra part that's going to be there. So this we can solve for using a separation variable. We can go ahead and separate the two variables over here. So di over I is equal to p of x multiplied by dx. So go ahead and integrate both sides. So that means that my function I that I'm looking for is supposed to be equal to the integral of px and dx. And then we have on the left-hand side, that's supposed to be the ln of I of x. Okay. Now in order to get I all by itself, then that means that I is equal to e to the integral of px dx. And that right there is going to be my integrating factor then. Okay. So that is what I'm going to multiply to both sides. Now, going back to what I have over here originally, just to kind of verify that, this guy right here, that is supposed to be my p of x, right? So if we now look at it as an integrating factor, I of x is equal to, according to what we said, e to the integral of 2 over x dx. So if I were to clean that up, that's e to the ln, 2 multiplied by ln of x, and then that 2 I can bring to the inside, so e to the ln of x squared, and there is your x squared that I'm just kind of pulled out of thin air to multiply to both sides then. So there it is. That's how we're going to be able to find that integrating factor. So we always look at this part right here, and our integration factor, I of x, is going to be e to the integral of p of x dx then. Okay, so now let's go ahead and try that with another example just to kind of show you how that actually works again. So here's an example of another differential equation that I would like to solve for. Now, first thing you should notice is that I don't have, actually I do have something in front of y prime, so that means I need to actually get rid of it. So first thing what I'll do is I'm going to go ahead and multiply both sides or everything by 2x. And careful that 2x is not the integrating factor. It's just to make it so that it's a form of a first order differential equation. So y prime plus 2xy is equal to negative x cubed multiplied by 2. Okay, so now let's go ahead and try to find that integrating factor. So I of x, the integration factor, is going to be equal to e to the integral of 2x dx, because this is going to be my p of x in this case. So that is going to be equal to e to the power of x squared, and that's what I'm going to multiply to both sides. Now, multiplying to both sides, the following, here's, well, let's go ahead and multiply that in. So take all of this right here and multiply by e to the x squared. If I do so, then I get e to the x squared, and then multiply by y prime. And note, again, I'm just going to draw them using different colors so you can see what's happening in each case. And then multiply by e to the x squared times 2x, and then we also have multiplied by y is equal to negative 2 times x cubed multiplied by e to the x squared. Okay, so that's what we get then when we multiply it out. On the left-hand side, you're supposed to recognize again that this is supposed to be the result of a product rule. So this guy is going to be like f, this guy is going to be g prime, and then this is going to be f prime, and then this is going to be g prime right here. It's going to be g, my fault. Okay, so let me go ahead and clean that up. So the result, because if this is going to be the product rules result, then that means the original function, or what you're trying to take the derivative of, is e to the x squared multiplied by y, and then prime. And all that is equal to the right-hand side, which is still going to be the same thing. So negative 2 times x cubed times e to the x squared. Okay. At this point, we're going to go ahead and take the antiderivative of both sides to get rid of that derivative sign. So e to the x squared multiplied by y, because the derivative and integral cancel each other out. The right-hand side, you need to integrate that thing right there. And hopefully you guys remember how to do integration by parts. So here, let me just go ahead and set that up on the side. So u is equal to something, dv is equal to something. So one you take the derivative of, the other one you take the antiderivative of. So the one where you take the antiderivative of, I think it's going to be the e function, because remember, u is something that you want diminished. Now be very careful about this part. You need to take the antiderivative of e to the x squared, but I need something to go along with that in order to compensate for the x squared, and that something is going to be the 2x right there, because I need to think about the chain rule. So if 2x goes along with the dv part, then that means that on the other side, there's not going to be much left. I'm going to take an x away, so that means that u should be equal to x squared then. So now we're going to go ahead and finish off this part. So du is equal to 2x, And then v right here, that is equal to e to the x squared then, going backwards using the chain rule. So now let's go ahead and write it out according to my integration by parts. So let's see. On the left, as we said, we're going to take the antiderivative. So it's just going to be e to the x squared times y is equal to uv. So that is going to be, oh, and there's a negative over there too. So let's go ahead and factor out the negative first just to make it a little bit easier. So this guy is from here. You're supposed to get x squared multiplied by e to the x squared, so that's the uv part, minus the integral of v du. So that's going to be 2x times e to the x squared multiplied by dx. And from what we have, it looks like we need to do integration one more time, but not by parts, but rather it's just a simple u substitution, or just chain rule in this case. So let's see, cleaning that up, we'll go ahead and keep the negative outside for the time being. So this is negative x squared multiplied by e to the x squared minus, for this part, we solved for it earlier. That's this guy over here. So that means the antiderivative is just e to the x squared then. And then now we're going to go ahead and say plus c because we technically solved for the antiderivative of everything. And my final step looks like it's just to divide that e to the x squared to both sides. So my final solution is y is equal to negative x squared minus 1. Actually, it becomes a plus 1. And then we have plus c multiplied by e to the negative x squared. And that's your solution to the differential equation then. All right. Well, thank you so much for watching. I will see you guys next time, and have a good one. All right. Take care. Bye-bye.